In our last video, we talked about projecting one vector onto another. In this video, we'll talk about projecting a vector onto a subspace. We'll decompose the vector into a part that is in the subspace and a part that is in the orthogonal complement of the subspace. Before we go into the decomposition, I'd like to talk a little bit more about the orthogonal complement of a subspace. Let's recall the definition of the orthogonal complement. Let W be a subspace of a vector space V. The orthogonal complement of W, which we denote W perp, is the set of all vectors that are orthogonal to each vector in W. Meaning if I take a vector in W perp and I take a vector in W and take their dot product, that dot product is always 0. One thing to note is that W perp is always a subspace of the vector space V. Let's check our three subspace conditions. First is the 0 vector in W perp. Well, let's suppose that I have any vector x in W. If I take the dot product of x with the 0 vector, I get 0. So that tells me that 0 is orthogonal to x. So 0 is in W perp. Next, I want to check that W perp is closed under vector addition. If I have two vectors x and y both in W perp, let's see if their sum is in W perp. Let's take z to be any vector in W. If I do the dot product x plus y dot z, I get x dot z plus y dot z. Now since x is in W perp, x dot z is 0, and since y is in W perp, y dot z is 0. So the dot product x plus y dot z is 0. That tells me that x plus y is in W perp. So W perp is closed under vector addition. Lastly, we want to check if W perp is closed under scalar multiplication. So let C be any scalar and let x be a vector in W perp. So I want to determine if C times x is in W perp. So let y be any vector in W. If I do C times x dot y, I can regroup things as C times x dot y. Now since x is in W perp and y is in W, I know that their dot product is 0. So I have C times 0, which is 0. So C times x is orthogonal to y. So we know that W perp is closed under scalar multiplication. So since W perp satisfies the three conditions of a subspace, we can conclude that W perp is a subspace of V. Now before we talk about orthogonal projections, we need the following lemma. Let B1 through BP be a basis for W. If a vector y is orthogonal to each of the basis vectors, then I can conclude that y is in W perp. So this lemma tells me that if I want to check if a vector is in W perp, I don't need to make sure that it's orthogonal to every vector in W, I just need to make sure it's orthogonal to each of the basis vectors. So to prove this lemma, I'll start with a vector y that's orthogonal to each basis vector bi. What I want to show is that if I have any vector in W, y is orthogonal to it. So let x be any vector in W. Since the vectors b1 through bp is a basis for W, I can write x as a linear combination of the basis vectors. So x equals c1 b1 summed up through cp bp. Now let's take the dot product x dot y. So if I rewrite x as a linear combinations of the basis vectors and then distribute, I get that this dot product is c1 b1 dot y summed up through cp bp dot y. Now since y is orthogonal to each of the basis vectors, each bi dot y is 0. So I have c1 times 0 summed up through cp times 0. And that's equal to 0. So this tells me that y is orthogonal to any vector x in W, which means that y is in W perp. So that concludes the proof of this lemma. Next we'll look at how to project a vector y onto a subspace W. Let W be a subspace of Rn. The orthogonal decomposition theorem here tells us how to take any vector y in Rn and write it as a composition of a vector in W and a vector in W perp. So let's go through this theorem. Again, let W be a subspace of Rn. Then any y in Rn can be written uniquely in the form y equals y hat plus z, where y hat is a vector in W and z is a vector in W perp. Furthermore, if u1 through up is an orthogonal basis for W, then we can find y hat by doing y dot u1 divided by u1 dot u1 times the vector u1 summed up through y dot up divided by up dot up times the vector up. And then the vector z can be found by doing y minus y hat. So y hat here is what we call the orthogonal projection of y onto W. If you look at the formula for y hat, you might see something familiar. This first term that we have here, y dot u1 divided by u1 dot u1 times the vector u1, we've learned previously that this is just a projection of y onto the vector u1. And the last term here, y dot up divided by up dot up times the vector up, is the projection of y onto up. So essentially what we're doing is we're taking y and projecting it onto each of the orthogonal basis vectors. Then we sum up each of those projections. So now let's try to prove this theorem. There are a few things we need to show here. First, we need to show that the formula that we gave for y hat actually gives me a vector in W. Then we need to show that the vector z obtained by doing y minus y hat is actually a vector in W perp. Finally, we need to show that the way we write y as a sum of a vector in W and a vector in W perp is unique. First, we know that y hat is in W because what we're doing is we're taking a linear combination of the vectors u1 through up. Since u1 through up are vectors in W, their linear combination is in W. So that's why y hat is in W. Next, we want to show that z is in W perp. And to do this, we're going to use the lemma that we proved previously. I'm going to take z and take the dot product with all of the basis vectors of W. Now, for any ui, do z dot ui. This is equal to y minus y hat dot ui. When we distribute, we get y dot ui minus y hat dot ui. So this gives me y dot ui minus the sum from j equals 1 to p of y dot uj divided by uj dot uj times the vector uj dot ui. Now, since the vectors u1 through up is an orthogonal basis for W, I know that the dot product uj dot ui is equal to 0 whenever j is not equal to I. So in the sum, the only term that remains is when j is equal to I. So we have y dot ui minus y dot ui divided by ui dot ui times ui dot ui. Now the ui dot ui's here cancel, so we're left with y dot ui minus y dot ui, which is just 0. So since z dot ui is equal to 0 for any ui, we know that z is orthogonal to all of the basis vectors. So by our previous lemma, we know that z is in W perp. Lastly, we want to show that this decomposition is unique. So suppose that we can write y as a sum of a vector in W and a vector in W perp in two different ways. So let's say y equals y1 hat plus z1, and also y equals y2 hat plus z2, where y1 hat and y2 hat are in W and z1 and z2 are in W perp. Since these are two representations of y, we can set them equal to each other. So we have y1 hat plus z1 equals y2 hat plus z2. Subtracting y2 hat from both sides and subtracting z1 from both sides, I get y1 hat minus y2 hat equals z2 minus z1. Since W is a subspace and y1 hat and y2 hat are both in W, I know that the left-hand side is a vector in W. Similarly, W perp is a subspace, and since z1 and z2 are both in W perp, I know that z2 minus z1 is also in W perp. Now, the only vector that's in both W and W perp is the 0 vector. So the left-hand side must equal the 0 vector and the right-hand side must equal the 0 vector. So we have y1 hat minus y2 hat equals the 0 vector, and z2 minus z1 equals the 0 vector. And this tells me that y1 hat equals y2 hat and z1 equals z2. So this shows that the two decompositions were the same to begin with, which means that the decomposition is unique. So that concludes the proof of this theorem. In our next video, we'll look at some examples of how this theorem is used.